So far we've talked a lot about the representation of probabilistic graphical models. We defined different classes of probabilistic graphical models, Bayes nets, Markov nets, and talked about their independence assumptions. Now let's operationalize probabilistic graphical models and figure out how to use this declarative representation to answer actual queries. It turns out there's many queries that one can use a PGM to answer, but perhaps one of the most commonly used one is what's called a conditional probability query. So let's define a conditional probability query. In a conditional probability query, we have some set of observations, little e, about a set of variables, big E. These are the variables that we happen to observe. We also have a particular query that we care about, which is usually, which we are going to denote as a set of variables y. So our goal here is to compute the conditional probability of the variables y given the evidence e equals little e, or a conditional probability. This type of query is useful for a variety of different applications. For example, in the medical or fall diagnosis domains that we've spoken about, we might have observations about certain symptoms or test results, and we're interested in predicting the probability of different failure modes or different diseases. In the pedigree analysis example that we also talked about, we might have observations about the phenotype or maybe even the genotype of some individuals in a family and are interested in reaching conclusions about other individuals. So unfortunately, like most interesting problems, the problem of inference in probabilistic graphical models is NP-hard. So before we talk about that, let's first remind ourselves what NP-hardness is. I'm not going to define it formally in this course, but as a rough intuition, if a problem is shown to be NP-hard, it means that it is extremely unlikely to have an efficient solution. Slightly more formally, it means that all algorithms that people have devised for this problem and a bunch of problems that are equally hard require at the very least time exponential in the size of the representation of the problem, which means that it's unlikely to be solvable for any problem that is bigger than a small handful of, say, variables in our context. So, which particular problems in the context of PGM inference are NP-hard? Well, first, the basic problem of exact inference in a PGM is NP-hard. So given a PGM P of phi defined by a set of factors phi and a particular target variable x and a value little x, computing the probability of the event x equals little x is NP-hard. In fact, even a simpler special case of this problem, one where we just want to figure out whether this probability is even positive, that too is NP-hard. So one might then say, well, okay, exact inference is intractable, but what about if we compromise a little bit on accuracy? What if we're just looking for an approximate answer? After all, we don't necessarily care about the 10th significant digit in this probability. Does that make the problem easier? Unfortunately, it turns out that the answer is no, and there's many different variants of NP-hardness results for approximate inference. This is just one of them. This one says that, again, given a PGM, an event x equals little x, and some set of observations, the problem of finding an approximate answer p for which we are guaranteed that this approximate answer is within epsilon of the truth is NP-hard. And this is true for any epsilon that's less than 0.5. And note that epsilon equal to 0.5 can be obtained by simply random guessing or guessing the value equal to 0.5. So any non-trivial approximation for this kind of conditional probability query is also intractable. So that's a rather depressing observation, and might want to make us give up on using PGMs for inference. But it turns out that one shouldn't get depressed too quickly because, importantly, this is a worst case result, which means we can construct these bizarre PGMs for which exponential time is the best we can do, but that doesn't mean that in the general case one can't do better. And the rest of the inference section of this course will be devoted to showing a variety of algorithms that, whether for exact inference or approximate inference, can do considerably better than this worst case result would suggest. So First, let's to understand where these results might be getting where these algorithms might be getting their power. Let's drill down into the inference question a little bit more. And here is a slightly elaborated version of our student network, where we now have additional variables. For example, the coherence of a course influences its difficulty, and a variety of other variables that we're not going to talk about. So inference in this model, and in general inference for probabilistic graphical model, uses the notion of factors that we've talked about before. And it turns out that it's convenient to use factors because it means that the algorithms apply equally well to Bayes nets and Markov networks, and it's a very useful abstraction. So let's think about this Bayesian network in the context of a set of factors. So here, for example, we had initially a prior probability over the C variable P of C. That translates into a factor whose scope is C. We had, for example, here P of G given I and D, and that translates into this factor whose scope is G, I, and D. And in general, each one of the CPDs in this network converts to a factor over the scope of the family, that is the variable and its parents. So now let's assume that our goal is to compute the probability of the variable J, and so we'd like to compute P of J. And what we see here is the joint distribution. So this is the joint distribution which we have defined using the chain rule for Bayesian networks. In order to compute P of J, what we need to do is only to eliminate or marginalize out all of the variables except for J. And so we end up with a summation that looks like this. Which is why this problem of inference, conditional probability inference, is often called sum product, because we have a sum over a product of factors. The inference problem for Markov networks takes exactly the same form. So here we have, once again, a product of factors. In this case, the factors are the form in which the network is originally defined. So we have the factors phi1 over AB, phi2, phi3, and phi4. And if we're interested in computing the probability P of D, then once again, we need to compute the product of these factors and then marginalize out. Now, but what I wrote here is not actually quite right, because the product of the factors isn't actually, in Markov networks, P of A, B, C, D. Rather, it's P tilde of A, B, C, D, which is a normalized measure. And in order to get the normalized measure, we need to normalize or divide by the partition function. So how do we deal with that if our goal is to compute P of D? Well, the point is that if what we have computed, if we ignore the partition function and rather we compute P tilde of D, we can infer that P of D is actually equal to 1 over Z P tilde of D, because the normalizing constant is a constant. And so if we've computed P tilde of D, we can obtain P of D by a simple process of renormalization of P tilde of D. What about evidence? Well, evidence, it turns out, can be done by a simple pre-processing step of factor reduction. So here, if we're trying to compute the probability of a set of variables y given evidence, that by definition is the ratio between the probability of y and the evidence divided by the probability of the evidence. And if we look at the numerator of this expression over here, and define a set of variables, define W to be all of the variables that are neither query nor evidence, then we can once again consider this as a sum product expression. So P of Y and E, we're going to introduce the variables W into this expression. So this probability over here is the sum of this probability marginalizing out the W. Now, if we now rewrite this expression over here, we can view it as a product of factors, and that's the case whether it's a Bayesian network or a Markov network. And that product of factors is only those factors which are only the components of those factors that are consistent with my evidence E equals little e, which means I reduce the factors by the evidence. So to understand what that means, let's look at this example over here. And let's imagine, for example, that we have an observation, say A equals little a, and we want to compute the probability of the distribution in the context of this observation. What that means is that we're going to take every single one of those factors, say A equals A0, we're going to remove from every factor that involves A the entries that correspond to A equals little a1, because those are not going to be consistent with our observation A equals little a0. Once we've reduced those factors to be consistent with those evidence, we have now still a product of factors, and we can go ahead and treat it in exactly the same way as we did before. And so we now have a sum over the variables W that need to be eliminated of the product of the reduced factors, and once again we can ignore the partition function by computing this probability and then renormalizing at the end. This applies equally well in the context of Bayesian networks. So here we might have, say, the observation I equals little I and H equals little h. So now this is no longer an equality, but rather because we have not yet conditioned on the evidence. And so if we want to make this equal, we have to reduce each one of the factors involving I and H based on the evidence. And so this turns into phi I of little I, which, as it happens, is a constant because there's no other variables in the scope. And similarly here and here. And for the H equals little h, we do the same thing, which in this case involves only this factor over here. And now it's back to being an equality. And if we want to compute the probability of J given I equals little I and H equals little h, we take this summation and renormalize, just like before. So to summarize, the sum product algorithm can be done as follows. It looks at, you convert the conditional probability into a ratio. That the numerator of this ratio is a product of reduced factors summed out over the remaining variables. The denominator of this is simply the numerator summed up over the variables, over the query variables y. And if we divide these two together, we realize that we can get away by computing simply this product of reduced factors and normalizing at the end. There are many algorithms for computing conditional probability queries. One of those involves pushing the summations into the factor product. This gives rise to an algorithm called variable elimination. It turns out to be a special case of a class of algorithms called dynamic programming. And it's a form of exact inference. A generalization of this algorithm performs message passing over a graph that also effectively deals with summations and factor product and factor summation. And there's many variants of this algorithm, some of which are exact and others are approximate. Here are some names of algorithms, only some of which we'll have an opportunity to discuss. And then finally, there's a very different class of algorithms that uses random sampling as the key technique, and it samples complete instantiations or assignments in a variety of different ways and uses those assignments to approximate the probability of a particular query. So here we have both exact and approximate methods, and this is an approximate method. And we'll talk about some of these in the remaining part of the section, of course. As we said, there's many different kinds of queries that one can use a graphical model to answer. Conditional probability queries are very commonly used, but another commonly used type of inference is what's called map inference. So what is map inference? Map stands as a shorthand for maximum a posteriori, and it's defined as follows. Here we have a set of evidence of observations, little e over some variables of e, and we have a query y. And it turns out that for computational reasons that we're not going to discuss for the moment, it's important that the set of y's is everything, all of the variables other than e. So now our task is to compute what's called the map assignment, which is the y, the assignment little y to the variables y that maximizes the conditional probability of the variables y given the evidence. Now, so for those of you who haven't seen the notation argmax is the y that provides the maximal value to this expression over here. Now, note that in some cases this maximizing value might not be unique. That is, there might be several different assignments, say y1 and y2, that give the exact same probability, and so the map is not necessarily a unique assignment. This has many applications, some of which we've discussed before. So in the context of message decoding, for example, where we have a set of noisy bits that are passed over the channel, over noisy communication channel, what we often want to get is the most likely message that was transmitted. That is an assignment to the transmitted bits that is the most likely given our evidence. In the context of image segmentation, we would like to take the pixels and figure out the most likely assignment of pixels to semantic categories. So both of these can be viewed as map assignment problems. Now, an important thing to understand about map is that it really is a different problem than conditional probability queries. So understand that, let's look at the following very simple example over just two random variables. So here we have a Bayesian network over the variables a and b, and if you multiply the two CPDs, you get the joint distribution shown over here, and it's fairly immediate to see that the map assignment is this one because it has the highest probability. Can we get at the map assignment by looking separately at the variable a and at the variable b? So if we look at that, we see that if we look separately at the variable a, the most likely assignment to the variable a is a1, as opposed to in the map assignment, the variable a took the value a0. And so one can't look separately at the marginal over A and over B and use that to infer the map assignment. And the reason is that we're looking for a single assignment over all of the variables that together has the highest probability. Unfortunately, just like the conditional probability inference, however, this problem too is NP-hard. So again, let's formalize what exact problem is NP-hard in this context, and so here's again one example of an NP-hard problem in the context of map, which is just to find the joint assignment with the highest probability. It's not the only NP-hard problem. Here's another one. Figuring out what for a given probabilistic graphical model and some threshold little p, whether there exists an assignment little x whose probability is greater than p. That problem too is NP-hard. So should we give up? Well, just like in the context of conditional probability queries, the answer is no, and there's algorithms that can solve this problem very efficiently, in fact, in an even broader set of problems than for conditional probability queries. So let's again look deeper into this problem and understand the foundations of what might make it tractable. So going back to our example of a Bayesian network, once again we're going to view CPDs as factors. So here P of C again translates into a factor over C, just like before. And whereas in the case of conditional probability queries, we wanted to sum out some of the variables, marginalize them, now we're going to find the argmax, which is the assignment to all of these variables, which maximizes the product. And so here we have a max of a product, which is why this is often called a max product problem. Let's break down the max product problem. So imagine that we, in the more general case, have a probability over y given e equals little e, and let's remind ourselves that y is the set of all variables other than the ones in E. And so by the definition of conditional probability, we have this ratio, where we're trying to find the maximal y that maximizes this ratio. And notice that the denominator is constant relative to y. Yes, with respect to y, which means that for the purpose of finding the maximal y, we don't really care about the denominator, only the numerator, which is the probability of y, comma, e equals little e, the unnormalized measure. This numerator, in the general case, is a product of factors normalized by the partition function, where the factors here are the reduced factors, reduced relative to the evidence. Once again, we notice that this is the partition function, and it's constant relative to y, which means that we can ignore it. And so once again we have that this expression is now proportional to a product of the same reduced factors. And so what we're trying to do is we're trying to maximize a product of factors in this more general case as well, which gives us the following as the optimization problem. There's many algorithms that can solve the map problem. The first is analogous to algorithms for sum product. These algorithms take the maximization operation and pushes that into the factor product, giving rise to a max product variable elimination algorithm. We also have message passing algorithms, which again are a direct analog to algorithms for sum product, and they give rise to a class of algorithms called max product belief propagation. However, because the map problem is intrinsically an optimization problem, one can also call on techniques that are specific to optimization. And the class of such methods include methods that are based on integer programming, which is a general class of optimization over discrete spaces. It turns out that this class of methods that build on integer programming techniques is one of the most popular methods in the last few years and has given rise to a whole new range of map algorithms that are considerably better than many of the previous algorithms developed up to that point, especially for the approximate case. It also turns out that for certain types of networks, that some of which we'll discuss, there are specific algorithms that are very efficient for that particular class of graphical model. And one of those, perhaps the most commonly used but not the only one, is methods based on a class of algorithms called graph cuts. And finally, because it's an optimization problem, one can also use standard search techniques over combinatorial search spaces, and there are problems for which this is also a very useful and successful solution. So to summarize, the map problem aims to find a single coherent assignment of highest probability, and that means that it is not the same as maximizing individual marginal probabilities, as we saw in the example. One can reformulate this problem as one of finding the max over factor product, and this is a combinatorial optimization problem which admits a whole range of different solutions, some of which are exact and others approximate. We've already said that there is many different algorithms for inferencing graphical models, but the simplest and most fundamental is an algorithm typically known as variable elimination. Let's consider the variable elimination algorithm in the context of a simple example of a graphical model structured as a chain. Here we have, we're interested maybe in computing the distribution over variable e, so we're interested in p of e, and as we've already said, that probability is proportional to the unnormalized measure p tilde over a, b, c, d, and e, summing up all of the variables except for e. So now let's see how we can do this more efficiently than simply constructing the joint distribution and then summing things out. So the first thing we do is we write up this unnormalized measure as a product of the constituent factors. And for the moment, we're going to assume that we only have pairwise factors for the edges in this graph. So we have a factor for AB, a factor for BC, CD, and DE. So those are the factors phi1 up to phi4. Now, what is the first observation that we have when we see the summation over A, B, C, and D of a product of factors? Well, we've already done this exercise previously when we were doing some proofs related to graphical models, that if we have a factor that doesn't mention a particular variable in its scope, we can move it out of the scope of the summation. So specifically, phi2 of BC can be moved out of the summation over A, as can phi3 of CD and phi4 of DE, which leaves us only with a summation over A of phi1 AB. So that gives us the expression over here. Now this is a summation over a pairwise factor, and the result of this is a factor over a single variable B, which we're going to call tau1 of B. And so we end up with an expression that looks like this. So now let's continue this developing this expression further. Noting that we now have an expression that doesn't involve A, only the variables B, C, D, and E, so that effectively we've eliminated A from our graphical model. So let's go back to this expression. We now have this product of 4 factors, and once again we can look at what factors involve the variable B and which ones don't, and the ones that don't can be moved out of the summation just as before, giving us this, where now we have an expression which is a product of these 2 factors summed out over B, and this is going to give us an expression tau2 whose scope is C. And so we now have an expression that does not involve the variable B, and so now we've eliminated B from this graphical model. And we can similarly continue to eliminate C and D, so that ultimately we'll end up with an expression that involves only the variable E, and that expression is going to be proportional to the probability of to the marginal probability of E. Now let's do this algorithm in the context of a somewhat more complicated example, which is our enhanced student network that we've played around with before. So let's imagine that our goal is to compute the probability of a variable J, this one, and in order to do that, we're going to have to eliminate from the joint distribution all of the other variables except for J. So this is our expression, and note that we have this product of factors. I've taken already in this expression the factors that were the CPDs and turned them into factors so that we can have a consistent notation, and now we need to eliminate every one of the variables except for J. So we're going to start with eliminating the variable C first, and so once again, we're going to take the summation over C and we're going to push it in, leaving in the summation only the factors that involve C. And those are phi d and phi c. Multiplying them together and eliminating c is going to give us a factor which we're going to call tau 1 and whose scope is d. Okay. And by putting tau 1 into this expression and removing the ones that we've just multiplied together, we end up with this expression over here. Having eliminated c, we now go ahead and eliminate d. So here we have the variable d, and which factors involve d? Well, tau 1 of d and phi g of gi and d. And so everything else is taken out of the summation, and we just have this expression over here. And that's going to give us tau 2, whose scope is g and I, after having eliminated the variable d from this product, whose scope is g, I, and d. And tau 2 gets put back into the bucket together with everything else. Moving forward, we're now interested in eliminating I. And so the factors that involve I are tau 2 of g and I, and phi s of s and I, and phi I of I. And so we go ahead and multiply them together to give us a factor whose scope is g comma I comma s, and eliminating I gives us a factor tau 3 whose scope is s and g. And so the process continues, and let's just finish it all the way to the end. Now our goal is to eliminate h. Well, h is a little bit of an interesting case. The only factor that mentions h is this factor, phi of h. And if we think about what phi of h is, phi of h, as it happens, is p of h given g and j. And so if we're summing that up over h, we're actually summing up what is, in fact, a conditional distribution. And since we know that a conditional distribution, when you sum up on the values on the left-hand side, the summation necessarily is equal to 1. So in principle, we could have taken this entire expression, erased it, and written 1 instead. And that would have given us something that is a factor that doesn't depend on anything, would have just disappeared. But for purposes of demonstration, we're not actually going to do that, because in fact, not every algorithm is clever enough to notice these kinds of coincidences. It depends whether they were designed to look for that. And so we're going to do this in the same way, in the same sort of naive way that we've done before, which is just to turn this into a factor which is going to be tau 4 of g comma j. So now we have that factor, which really is 1, but we're not going to pay attention to that particular aspect for the purposes of demonstrating how the algorithm would work. Okay, next is eliminating g. And we have this expression, which we inherited from the previous slide. And g is one of the big ones because it appears in phi L, tau 3, and tau 4. So when we think about the variables here in the scope, we see that this one actually has this product over here, actually has a scope of L, comma G, comma S, comma J, which is the largest factor, the one with the largest scope that we've encountered so far. Summing out G, we end up with a factor whose scope is L, S, and J, so we're missing an S. And now we put that into this expression, and out comes a now product of 2 factors. And really at this point, we may as well just multiply them and end up with a factor over J and move on. So that gives us variable elimination in its naive form. What about variable elimination with evidence? Well, we've already basically established how to deal with evidence. If we're interested in, for example, solving the query probability of j, comma I equals little I, comma h equals little h, the way in which we do that is by computing the probability of the joint event j, comma I equals little I, comma h equals little h. And the way in which we do that is by reducing the factors to correspond to this scope. And so if these were, so we take each of the factors that involved I and we basically instantiate it to take a particular value for that I, the value little I, and similarly for h. And so we see here, for example, that whereas phi I initially depended on I, now it doesn't depend on anything because this is simply the value phi I of little I, which is a constant. And whereas, for example, G depended on D and I, as we can see in the original diagram, here phi G in the reduced factor doesn't depend on I and is really probability of G given little I and D. And the same reduction occurs for H equals H, and so we end up with the following set of reduced factors. And now once we have that set of reduced factors, we do elimination as exactly as before. No changes whatsoever to the algorithm. The only aspect that's a little bit different is notice that we don't eliminate no h and no I because there's no point eliminating a variable that has a single value. There's no need to sum up over it when it only has a single value. So this gives us a unified framework for dealing with queries, whether they involve evidence or not. And then how do we get the probability of J given the evidence? Well, this is straightforward. We simply renormalize. Because we can take this and simply divide by what it turns out to be the probability, the normalizing constant is okay. So let's see whether the same idea applies to Markov networks. So here's our simple Markov network with 4 variables. Let's imagine that our goal is to compute P of D. And so in order to do that, we need to eliminate A, B, and C from the unnormalized measures. So we have this being the unnormalized measure, and we're summing up over A, B, and C. And the process works in exactly the same way. So if we want to sum out A first, then here is the factors that involve A, phi 1 of AB, this one, and phi 4 of AD. Multiply them together, we get a factor whose scope is ABD, and then we sum out A to get a factor whose scope is BD. That gives us a new set of factors where A has effectively been eliminated from the graphical model. And at the end of the process, we get a factor over the single remaining variable D, so tau 3 of D. And that factor is not the probability of D. It's proportional to the probability of D. It's actually equal to P tilde of D, which is the unnormalized measure. And so in order to get P of D, we renormalize. So to summarize this, the main routine in this algorithm is a routine which we call eliminate variable z from a set of factors phi. And what it does is the following. We first look within phi, and we define a set of factors phi prime, which are all factors that involve z. And that's what this mathematical expression says. The factors phi I such that z is in their scope. We take all those factors and we multiply them. And then we sum out the variable z, which is the one that we want to eliminate. Now, and here is the important point. we've already used up these factors. These ones over here have now been used. We don't want to reuse them. And so we take them out of the set of factors, and instead we introduce the one that we just created by multiplying those factors and summing them up. This basic operation is what we use in the context of the algorithm as a whole. We begin by reducing all factors by the evidence, which is just eliminating the rows that that are not consistent with the observations. And that is what gets us our set of factors phi. Now, for each non-query variable, we need to eliminate it. And so we run one at a time something that eliminates the variable z from the set of factors phi. Each such step changes my set of factors. It adds factors and removes, so actually starts by removing factors, which the phi prime from the previous line, and it adds a new factor tau. And then finally, at the very end, when all variables have been eliminated, there may be one or more factors remaining. So at that point, we multiply all of the remaining factors and then renormalize to get a distribution. So to summarize, this is a very simple algorithm. It works equally well for Bayes nets and Markov nets. And it uses a factor product and factor summation steps. And it does that by ensuring that when you sum out a factor, when you do the summation step over a variable z, then all factors involving z have been multiplied in, which is the critical piece of the correctness of this algorithm. So we've previously presented the variable elimination algorithm. Now let's think about what is the computational complexity of this algorithm. So let's first look at the basic operations that are used when we do an elimination step. And there's these two basic operations. There's the factor product and the actual marginalization. And so what we're going to do now is we're going to count the operations used by each of them. So let's start with the factor product. And first, let's remind ourselves what factor product is doing. So factor product is taking, in this case, for example, a factor whose scope is AB and one whose scope is BC, and producing a factor whose scope is ABC. Now, let's think about how each of the numbers in this result is produced. So each of these is a product, in this case, of two numbers, one that comes from this table and one that comes from that table. So we have to produce every one of the rows in this new table, in this new factor. So let's call nk the number of the rows in this new table. And how many operations are there that we need to produce each such row? Well, if we need to multiply in this case, mk different factors, so for each row, we have mk minus 1 product. And so total, we get mk minus 1 times nk multiplications. Now let's look at the factor marginalization. So here we had a factor whose scope was xk. We summed out z, and we end up with a factor whose scope is 1 less. So again, let's remind ourselves, this is a marginalization, in this case, over b. So marginalize b. And we see that each of the rows in our output is produced, in this case, by a summation of 2 of the rows in the original factor. But if we turn this on its head, we also see that each row, so each number in this factor is used exactly once. Each one gets added to only one of the rows in the new factor. And so a simple upper bound on the amount of additions that we need to do is simply the size of this factor nk. So now let's total up the computational complexity of variable elimination. So let's assume that we start with m factors. For Bayesian networks, m is really effectively n, because we have one factor for every variable. which is the CPD. And the reason I wrote less than or equal is because of the reduction by evidence. Now, for Markov networks, it can actually be larger. So if you think of a grid Markov network or a fully connected Markov network, the number of factors might be, so fully connected pairwise Markov network, the number of factors can actually be larger than the number of variables. So that's why we have the complexity in terms of M as opposed to in terms of N. Now, so that's the set of factors that we start out with. And then what happens as we do an elimination step? An elimination step takes some of those factors and generates another factor. But each elimination step generates exactly one factor. How many elimination steps do we have? Well, each elimination step corresponds to an elimination of one variable, so we have at most n elimination steps. So the total number of factors that we ever produce is, which we're going to call m star, is going to be equal to at most m, which is the set of initial factors, plus the newly generated factors, which is at most n. And so altogether, m star is less than or equal to m plus n. So now that we've figured that out, let's look at what the complexity of the algorithm is in terms of various key quantities. So n is the size of the largest factor that I ever create, which is the max of these different nks that I had. So now how many product operations do we have? Well, remember that we had a sum over different elimination steps, so sum over k, and this was the number of product operations that we have. But now here's the critical observation. Each factor is multiplied in at most once. Because as soon as we multiply it in, it goes away. Which means that the sum over k, mk minus 1, is at most the total number of factors. And so, said otherwise, we can write that this is less than or equal to n times the sum over k, mk minus 1, and this is less than or equal to m star. Because this is at most the total number of factors in my universe of factors. What about the number of summation operations? Well, here, this is less than or equal to the sum over k and k, which is n times, less than or equal to n times the number of elimination steps, which is simply less than or equal to n times n. So altogether, between these two steps, over here we have n times m star, over here we have n times n, which tells us that the total work that we have is linear in n and in m star. Great, linear time, aren't we lucky? Well, not quite, because the nk, which is the contribution to this quantity n, is the total number of values in a factor. And so if we say that, for example, just for simplicity, all variables have d values in their scope, so that, for example, all variables are binary, that would be d equal to 2, for example, then the number of values in a factor is exponential, where the base of the exponent is d, and the exponent is the cardinality of the scope of the kth factor. That is the number of variables in the kth factor. And so this is, over here, our big source of exponential blowup. So let's understand how this complexity manifests in the context of a real example. So this is the run of variable elimination that we did before. I've just written it out all in one slide. And so now let's see what the complexity of this is, we see that we have produced several factors here, and let's write down how many variables are in the scope of each of these factors. This one has 2, this one has 3, G, I, and D. This one has 3, S, G, and I. This one has 3, H, G, and J. This one has 4, L, G, S, and J. And this one has 3, J, L, and S. And so the size of the largest factor is this one that has 4 variables in it. And that is what's going to, in general, drive the complexity of the algorithm. Not in an example as simple as this, but in more realistic examples. So now let's understand how elimination ordering plays into this. We've previously said that variables can be eliminated in any order, so long as we're careful about multiplying things in at the appropriate time. But now let's see how elimination order might affect the complexity. So assume that in this example, I'm going to make a not very judicious decision, and I'm going to start by eliminating G. So which factors do I need to multiply in order to eliminate G? Well, phi L of L and G, phi G of G, I, and D, and phi H of H, G, and J. And so if I multiply all these together, it turns out that I now end up with a factor whose scope is, let's see, L, G, I, D, H, and J. So a total of 6 variables. Whereas before, the largest factor that we ever generated had 4 variables. So that's maybe, you might say, 6 versus 4, not a big deal. I mean, it's, you know, how much difference does it make? So let's convince ourselves that in other graphs it might make a bigger difference. So here's a graph that has, it's a simple pairwise Markov network with A and C and then a bunch of variables in the middle, B1 up to BK. And imagine that I start by eliminating A first. Well, what are the factors that involve A? Well, we have a factor AB1, AB2, AB3, up to ABK. And the total scope of the factors of this factor that we generate is going to be A, B1, up to BK. So it's going to be exponential in K. So the size of the factor is exponential in K. Maybe this is inevitable. Well, no. So let's imagine that instead we're going to eliminate the BIs first. So let's think, for example, that we're going to start by eliminating B1. Well, B1 is in a factor with A and in a factor with C. So we're going to end up with a product of, say, phi A1 of A comma B1 times phi C1 of C comma B1. And that's going to give me a factor whose scope is A, B1, and C. And the result of summing out B1 is going to be a factor tau 1 of A and C. We're going to get the exact same behavior when we now eliminate B2, and that's going to give me a factor tau 2 of A and C, and so on and so forth, until at the very end I'm going to have a bunch of factors tau I of A and C that are all multiplied together. And I've done this without ever generating a factor whose size is bigger than 3. So to summarize, the complexity of variable elimination is linear in the size of the model, the number of factors and number of variables, and more importantly, in the size of the largest factor generated during the course of variable elimination. And unfortunately, that size is exponential in its scope. And that is the thing that drives the complexity of variable elimination. And we've also seen that the size of this factor is something that depends heavily on the elimination ordering, which means that choosing a judicious elimination ordering is important. Very important insights about variable elimination and how to best pick the elimination ordering is provided by thinking about the operations that variable elimination executes as operations on a graph. So let's see what that does. So let's consider the initial graph in our example, and let's first view this graph in terms of the factors that it involves. So if this is the set of factors that we have in our analysis, viewed as undirected, viewed as simply as factors. So what is the structure of the graph that corresponds to this set of factors? Well, first we're going to make all of the edges undirected, but that's not enough because we see, for example, that we have a factor here, which is a factor over g, I, and d. And so what we need to do is we need to add an edge between I and d to represent the fact that they're together in a factor. Other examples, other cases where we need to do this correspond to the other V structures that we have in this graph. So here, for example, we have a V structure involving J, so we're going to need to connect J's two parents, and similarly for H's two parents. This step, by the way, is called, not by me, moralization, because of the dubious moral value of marrying the parents of a child, no matter how many of them there are. And so I did not invent that name. So having moralized the graph, we now have this version of it. And this is what we previously defined to be the induced Markov network for the current set of factors. So now let's think about a variable elimination step and what it does to this graph. So let's begin by eliminating C, and if you remember, that involved this operation. And so first, eliminating C is changing the set of factors. It removes these two factors over here from the set and introduces a new factor, tau 1 of D. So the induced graph is now going to look like the following. We've taken C out, and the remainder is the induced graph over the set of factors. Okay? Now we're going to continue. We're going to eliminate D. So once again, we're going to take the two factors that we've now introduced, these two factors that are involved here, which is tau 1 of D and phi G of Gi and D, going to multiply them and going to eliminate D. And so the resulting, graph is now going to look like this, where again the nodes with the dashed edges are not really there. They're just there to remind us that they were there before. Continuing on, we're going to eliminate I, and that involves multiplying in this term, and this term. And now something interesting is going to happen. The factor that we introduced, which is tau 3 of S and G, is a factor that doesn't have an edge in the current graph. So if we're interested in having this graph represent our current set of factors, we're going to need to introduce this edge between G and S, because that edge is necessary because S and G are together in the same factor. So that edge is called a fill edge. It's an edge that I had to introduce because of the elimination ordering. So one way to think about this is using the following example. Imagine that every variable that's eliminated is going off on a trip around the world. And when it's doing that, it's throwing a big goodbye bash and inviting all of its friends to come and join it. And when it does that, all of its friends get to meet each other and say, oh, you guys are nice. I'm going to be your friends too. And so all of the friends of the variable that's eliminated become friends as a consequence of the elimination step. Okay? So let me write that down. All variables connected to, in this case, I, become connected after it's eliminated. So become connected directly. And that's a general consequence of the elimination step process. It's just that the previous ones didn't happen to introduce fill edges. Okay, let's continue. So now we're going to eliminate H. H also doesn't introduce any fill edges, and so we're going to end up with that. And basically the remaining steps are pretty mundane. We're going to eliminate G, L, and S, and we're going to end up with the following graph. So this particular variable elimination process only introduced one fill edge, which is a fairly conservative thing, and shows that we selected a pretty good elimination ordering in this case. So we can now take and put all of these edges that we ended up using together in a single graph, and that graph is called the induced graph. And the induced graph, which is denoted I for induced, phi comma alpha, over a set of factors phi, and induced by particular ordering alpha, because you remember that we were getting different complexities and we're going to have different fill edges depending on the order in which variables are eliminated. So this induced graph has the following properties. It's an undirected graph where we connect every pair of variables xi and xj if they ever appeared in the same factor when we ran variable elimination using alpha as the ordering. And so in this case, all of the black edges were there to begin with, and we ended up introducing just one of those additional new or fill edges. So now there's some interesting properties of the induced graph that are worth noting. First of all, there's properties that relate factors produced during variable elimination and cliques in the induced graph. So first of all, let's define what a clique is. A clique is a maximal fully connected subgraph. So let's parse that too. So for example, DIG here is a fully connected subgraph because all of its three nodes are connected to each other. And it's maximal because I can't add any other variable to this and still have that property to hold. So if I try and add S, for example, then S is not connected to D. If I try and add C, C is not connected to I or G. So I can't add any other variable to this particular clique. So it's a clique. Here's a clique that's not maximal. So it's not a clique. So GLJ is a fully connected subgraph, but it's not maximal because I can add S and still have that hold. So here is another clique in this graph. So we have GID being one clique, GS, L, and J being another clique. We're going to have a third one, which is G, S, and I. Another one, which is CD. And let's see if I have enough colors to do this. And a final one, which is G, H, and J. And if we now look at the factors that we produced in the course of variable elimination, we see that there is an exact correspondence between the factors and those cliques. So here, for example, the yellow one is CD, which is this one over here. This one over here, which is GID, is the red one, this one. So that's the red one. This one has SIG, so that's the green one, this one. This one is HGJ, which is the brown one. Tau 5 induces the big factor, the one that involves 4 variables, and that's the blue factor over GS, L, and J. And this one doesn't actually introduce any new cliques, which is why it doesn't have any cliques associated with it. So every factor produced during variable elimination is a clique in the induced graph. we can equally well check, and we saw that in the previous slide already, that every maximal clique in the induced graph is a factor that's produced during variable elimination. So we've demonstrated this to ourselves by inspection, but let's actually do a proof of this. So let's consider a maximal clique in this induced graph. So let's consider, for example, G, S, L, and J. So that's a maximal clique. And now let's consider the run of variable elimination. And one of those variables has to be, the one to be eliminated first. So some variable in this clique is first to be eliminated. Well, what happens when a variable is eliminated? Once it's eliminated, it doesn't have any more edges that get added to it. So once a variable is eliminated, it has no new neighbors are added to it. Which means that at the time that it was eliminated, it had all the neighbors that it had in the clique. All the clique members as neighbors. But if that's the case, then it means that it had factors involving all of those other guys. So it participated in factors with all these other guys. And that means that when I multiply them all together, we're going to end up with a factor over all of them. And that is a proof that every maximal clique in the induced graph must correspond to a factor produced during the variable elimination algorithm. So now that we've constructed a graphical view of variable elimination, we can go ahead and construct a measure of the complexity of variable elimination. And that is a measure known as the induced width. So first, we're going to define the width of an induced graph is the number of nodes in the largest clique in the graph by convention minus 1. Why minus 1? No good reason, but that's what people, that's the definition of induced width. The minimal induced width of the graph is the minimum over all possible elimination orderings alpha of the width of the induced graph. So this is the best achievable complexity that one can aspire to with any elimination ordering. You can think of the minimal induced width of the graph as a lower bound on the best performance of variable elimination for any model that factorizes over the graph K. In summary, we've seen that the variable elimination algorithm can be viewed quite intuitively as taking a set of steps, each of which transforms the graph. Specifically, a variable elimination step for a variable x takes all of x's neighbors that may or may not have been connected before and connects them to each other. The result of all this is something called the induced graph, and we've seen that the induced graph is possibly quite connected as a result of this variable elimination process, and that the cliques in this induced graph, that is the maximally connected subsets, maximally fully connected subsets, correspond directly to the complexity of the variable elimination algorithm, and as we'll see, can therefore help us analyze its computational properties. When we discussed variable elimination, we said that variable elimination is correct no matter the elimination ordering that's used, but we also showed that the elimination ordering can make a very significant difference to the computational complexity of the algorithm. So that begs the question of how we find a good elimination ordering. Fortunately, the computational analysis based on graphs that we recently did gives us an intuition into how to find good elimination orderings, because it turns out that the notion of an induced graph and the way in which it indicates the complexity of variable elimination can allow us to construct good methods for finding elimination orderings with good computational properties. How good of an elimination ordering can we construct? So here is yet another example of the fact that any interesting problem is NP-hard. So the following problem is NP-hard also. For graph H, determining whether there exists any elimination ordering alpha for which the induced width is less than or equal to some fixed value k, that problem is NP-complete. So you might say to yourself, well, that's not surprising. I mean, probabilistic inference is NP-complete, so obviously finding a really good elimination ordering is going to be NP-complete. Turns out that this is a separate NP hardness problem. That is, even if you could solve this problem, even if somebody gave you the best elimination ordering, you're still going to have graphs for which the width is sufficiently large so that you can't actually solve the problem in polynomial time. So finding the best induced width, or the elimination ordering that gives you the best induced width does not give you polynomial time performance in general. And so these are two separate NP-hard problems. So how do you find a good elimination ordering? Fortunately, simple heuristics actually do pretty well. So one standard way of finding good elimination ordering is to simply do a greedy search, eliminating one variable at a time, where at each point in the elimination, you use some kind of heuristic cost function to decide which variable you're going to eliminate next. And there's some obvious cost functions to use, and it turns out that surprisingly they work pretty well. So, for example, one cost function is what's called min neighbors, which is to pick the node that has the minimal number of neighbors in the current graph. So you want to pick the variable that's connected to the fewest friends so that it has the smallest party or produces the smallest factor. So this corresponds to the smallest factor, or the one whose cardinality is smallest in terms of number of variables. Min weight accounts for the fact that sometimes you have variables that have 100 values and others that have 2 values. And if you just count variables, you're going to ignore that distinction. So min weight computes the weight, or the total number of values in the factor formed. So min weight is a way of capturing the fact that if you have 2 variables, each of which has 100 values, you might prefer to nevertheless pick a factor that has 5 variables, each of which has only 2 values. So these just look at the size of the factors formed, and they ignore the fact that some of these factors might be inevitable. So a different strategy is to look at how much extra work is caused by the elimination ordering. So min-fill is a strategy that says, if I eliminate this node, how many nodes that weren't friends before become friends due to this elimination step? So here, basically, I'm counting added complexity above and beyond the complexity that I would have had from the edges that I previously generated. And finally, again, you have a weighted version of the fill heuristic that takes into account not just the number of edges, but also how heavy they are. That is, how big are the, what's the domain size of the variables that they connect. And it turns out that min-fill, which is actually quite often used in practice, is a pretty good heuristic. Now, one important way of understanding the issues of finding elimination orderings is by looking at the following result. And the result tells us that the induced graph that is produced by variable elimination, regardless of the elimination ordering, is triangulated. Now, what does triangulated mean? Triangulated means that you cannot have a loop of size more than 3 that doesn't have a bridge, an edge that goes in one direction or another, so that there's a way of crossing across that loop without going all the way around. Let's convince ourselves that this is true. So here's a simple proof. So once again, consider a set of variables and assume by contradiction that there is a loop like this. So for example, assume that we have a loop of size greater than 3. And again, one of these variables has to be the first to be eliminated. So assume that C is first to be eliminated. Well, once we eliminate C, we end up introducing an edge between B and D. And so there has to be an edge between those two neighbors of C. Because when C is eliminated, the CD edge must exist. The CB edge must exist, because as we've observed before, you don't add any neighbors to C once you eliminate it. And so at that point, a fill edge must be added. So it turns out that one way to find an elimination ordering, an alternative to the heuristic that I mentioned earlier, is to find a low-width triangulation of the original graph. And there's been a lot of work in the graph theory literature on triangulating graphs, which we're not going to talk about, but it turns out that you could use all of that literature for finding good low-width triangulations and then use that for constructing an elimination ordering. So now let's convince ourselves that this can make a big difference. So let's consider a practical application. And this is an application to robot localization and mapping. So what we're going to see here is a robot moving around. And at each point in time, it sees several landmarks. And it knows which landmarks it sees. It can recognize them. And what it senses at each point is some kind of approximate distance to the closest landmark. So let's write that down as a graphical model. The graphical model looks something like this. We have at each point in time a robot pose, which is the robot pose at time 0, 1, up to the end of the trajectory, t. And we have a set of landmarks whose positions are fixed. The landmarks don't move. So notice that these are not random variables that change over time. They're just there and they're constant. And what you see here in gray are the observations. So this, for example, assumes that at time 1, robot saw landmark 1. And so what we have here is the observation. The observed distance is a function of the robot pose and the landmark position. And here at time 2, we have that the robot saw landmark 2. So we have this dependency over here. And at time 3, the robot also saw landmark 2. So you have 2 observations for the same landmark. In here, I didn't draw the fact that you could actually see the same landmark. Sorry, you can see more than one landmark at a given point in time, but that also is easy to add in. Okay. So now, if we take the previous robot trajectory that we saw and we write down the Markov network that represents the factors, we see that we have these light blue little dots that represent the robot pose at every point in time. We see that we have these temporal persistence edges that represent the fact that the robot pose at time t is correlated with its position at time t plus 1. And we have these dark blue robot pose variables that, sorry, these dark blue landmark position variables, where we see that a landmark is connected to all of the positions at which it was visible by the robot. And this is an edge that's induced by the V structure that we have over here. So this is an edge that's induced by this V structure, which we have because Z1's been observed. Okay? So does elimination ordering matter? Oh boy. This is what you get when you eliminate the robot poses first and then the landmark. And this, what you see here, is the induced graph. And you can see that you get this huge spaghetti where most of the landmarks are connected to all other landmarks. Okay, what about a different elimination ordering? This one's already better. This is what happens when you eliminate landmarks and then poses. And you see the induced graph that you get over poses. And you can see that it's still pretty densely connected, but it's not nearly as bad as the spaghetti that we had before. And finally, let's look at the result of min-fill elimination. So this is what you're seeing is the fill edges being constructed. And you can see that it's actually very sparse. Let's look at it again. Very few fill edges are actually added over the course of the trajectory. And so the elimination ordering makes a very big difference. In summary, we've seen that finding the optimal elimination ordering is an NP-hard problem, and that it is an NP-hardness that is different from the intrinsic difficulty of inference in graphical models. However, we've also shown that the graph-based view of variable elimination gives us a set of very simple and intuitive heuristics that allow us to construct good elimination orderings. And those work by looking at the induced graph as it's constructed in the course of variable elimination and trying to keep it small and sparse. These heuristics, although simple and certainly potentially not providing not good performance in the worst case, are often quite reasonable in practice and are very commonly used.